So afterwards, I'll change my name. Okay.
Okay.
Okay. Today we are going to do Ascali's theorem, Unit 9. So already we have discussed about convergent sequences. When do you say that a sequence is convergent? If d of xn comma xn tends to 0 as n tends to infinity. Or how you define this? For given epsilon greater than 0, there exists a delta greater than 0 such that mod xn minus x is less than epsilon whenever or for all n greater than or equal to m. Then we say that the sequence is convergent. Okay, can you give some examples of convergent sequences? Suppose we know the sequence 1 by n square. That is, for given epsilon greater than 0, there exists a delta greater than 0 such that 1 by n square minus 0 is less than epsilon, or we can say that limit tends to infinity 1 by n square is 0. So that we say that the sequence 1 by n square is convergent. Okay. Now here, suppose we are going to define a sequence when it is a Cauchy sequence. Suppose X is a metric space. X is a metric space with the metric D. With the metric D. So we say that the sequence Xn is a Cauchy sequence if D of xn comma xm tends to 0 as n comma m tends to infinity. Or we say that D of xn comma xm less than epsilon for all n comma m greater than delta. So in any metric space, actually first important theorem is in any metric space, every convergent sequence is a Cauchy sequence. In any metric space, x, any every convergent sequence is a Cauchy sequence. So how you prove, suppose, see generally how you prove a sequence. Suppose xn be a convergent sequence. Now I prove that xn is a Cauchy sequence. Always analyze two things, what is given, what we have to prove. By making use of xn is a convergent sequence, we prove that xn is a Cauchy sequence. So xn is convergent means suppose xn converges to x. So what do you mean? For given epsilon greater than 0, there exists a positive integer m greater than 0 such that d of xn comma x is less than epsilon by 2 for all n greater than or equal to m. And okay, and suppose because in place of n, if you take n, you get d of xm comma x is also less than epsilon by 2. So then tell me what is d of xn comma xm? You can write it as this is less than d of xn comma x plus d of x comma xm, which is less than epsilon by 2 plus epsilon by 2, which is epsilon. So whenever d of xn comma x less than epsilon by 2, in place of n, if you take, see, this is also for m greater than or equal to n, you can have d of xm comma x is also less than epsilon by 2. So d of xn comma xm, which is less than d of xn x plus d of x comma xm, which is less than epsilon. Therefore, the sequence xn is a Cauchy sequence. In any metric space, every convergent sequence is a Cauchy sequence. How you prove? Suppose xn be a convergent sequence. Write the definition of convergent sequence. What is that? Whenever the sequence xn converges to x for given epsilon greater than 0, there exists a positive integer. Already we are using this m, no? Let us take another integer to avoid confusion. There exists for given epsilon greater than 0, there exists n naught greater than 0 such that d of xn comma x is less than epsilon by 2 for all n greater than or equal to n naught. So if you replace n with m, you have for all m greater than or equal to n naught, d of xm comma x is also less than epsilon by 2. Therefore, d of xn comma xm is less than d of xn x plus d of x comma xm, which is less than epsilon. Therefore, xn is a Cauchy sequence. Every convergent sequence is a Cauchy sequence, and also every Cauchy sequence is also a convergent sequence. That means, and we have every Cauchy sequence is bounded. And why every Cauchy sequence is bounded? Because generally we are writing in terms of metric. What is this metric? In real numbers, mod xn minus xm is less than epsilon. So you take K1 is minimum of, you have, right, take x1, x2, etc., xm minus 1. Okay, Andy? Like that you take. K2 is maximum of x1, x2, etc., xm. xm minus 1. Okay, then what you will get? You have k1 less than or equal to this xm less than or equal to k2 for all n greater than or equal to n naught. Therefore, what do you mean? Every Cauchy sequence is bounded. Okay, Andy? So a metric space is said to be complete. Every Cauchy sequence in it converges. If every Cauchy sequence in a metric space converges, then we say that, because you can say 1 by n is a Cauchy sequence, and 1 by n is a convergent sequence, but it is a Cauchy sequence, but it is not convergent. So there are some Cauchy sequences which are not convergent. Therefore, we can say that a metric space is complete. A metric space is complete if every Cauchy sequence converges in it. So you have to remember. And the next one is, next theorem 9.3.8. This is one important theorem. In any metric space X, in any metric space X, a Cauchy sequence is convergent. A Cauchy sequence is convergent if and only if it has a convergent subsequence. If and only if it has a convergent subsequence. Hello students, today is Ramya is able to join. Yesterday she was asking for admission number. Hello? Are you listening? Hello, anyone
Yes,
is there?
yes, ma'am.
Yes, ma'am.
Are you able to follow?
Yes, ma'am. Yes, ma'am.
So we have to prove sequence xn is Cauchy if and only if it has a convergent subsequence. A convergent subsequence. For this, we proved that every convergent sequence is Cauchy. If Cauchy sequence is convergent, suppose if xn is convergent. When you say that a sequence is convergent, if and only if it has a convergent subsequence. Okay, now? Convergent subsequence. So if xn is convergent, it has a convergent subsequence. Conversely, suppose that xn has a convergent subsequence. Suppose xn has a convergent subsequence. Then what is required to prove? Required to prove is xn is Cauchy. xn is a Cauchy sequence.
Excuse me, ma'am. I missed actually in the beginning. So xn has a convergent subsequence, but how do we know if xn has a convergent subsequence?
xn has a convergent subsequence means, suppose that means every convergent sequence, if xn is convergent, then only it will have a convergent subsequence. Okay.
Okay.
Yeah, sequence
what-
xn is convergent. That means, suppose if you take any sequence, for example, you take geometric sequence 1 by 2 power n. Okay.
Mm-hmm.
So it is convergent. If it is convergent means it will have some convergent subsequences like this. Suppose if you take 1 by 2 power 4, 2 power 6, this is a convergent subsequence of this. So every convergent sequence will have a convergent subsequence. Yes, tell me now. You ask your doubt.
Okay.
Okay.
Yeah.
Actually, we are going to prove at what relationship between the compactness and completeness. Okay. When do you say that a metric space is a complete metric space? Complete metric space means every convergent that means every Cauchy sequence should be convergent. Actually, at basic level, we have learned that a sequence is Cauchy if and only if it is convergent. Okay. So generally, just I'll give you an idea. See, suppose if you take xn, if mod xn minus xm is less than epsilon for all n comma m greater than or equal to some n naught, then we say that the xn is a Cauchy sequence. So you have every Cauchy sequence is convergent. Why? Because you take if you add and subtract one xn minus x plus x minus xm. Okay, so this is less than or equal to mod xn minus x plus mod xm minus x. So this is less than epsilon by 2 plus epsilon by 2, which is epsilon. What do you mean by that? You have, whenever a sequence xn is convergent, you have mod xn minus x is less than epsilon by 2 for all n greater than or equal to n naught. In place of n, if you take m, xm minus x is also less than epsilon by 2. Am I right? For every m greater than or equal to n naught. So you take n naught is some n is the minimum of n and m, whatever it may be. If you take a mod xn minus xm is less than epsilon by 2, means you have mod xn minus x plus x minus xm is less than epsilon. That means, what do you mean by this? Every convergent sequence is Cauchy. Every convergent sequence is a Cauchy sequence. Now, what I am proving is a Cauchy sequence is convergent if and only if it has a convergent subsequence. Okay. Now, every convergent sequence is Cauchy and Cauchy sequence is also convergent. And that by how you are proving? Because if it is a Cauchy sequence, by above argument, every Cauchy sequence is bounded. Every Cauchy sequence is bounded. And we know that every bounded sequence will have unique limit point. That means you have, if it is a Cauchy sequence, you have limit n tends to infinity, xn is L, and this L is unique. So that is the reason whenever limit n tends to infinity, xn is L, the sequence is convergent. Every Cauchy sequence is convergent. Okay. And next one is, next theorem is a subspace Y of a complete metric space. A complete metric space X is complete if and only if and only if Y is closed. Y is closed in X. When do you say that a set is closed in X? If it contains all of its limit points. If it contains all of its limit points, then we say that the set is closed. So now we prove that a subspace Y of a complete metric space X is complete if and only if Y is closed in X. Suppose, see here, first part you take Y is complete. What do you mean by Y is complete? We have to prove that Y is closed in X. For that, what we have to prove? We prove that Y bar is equal to Y. Then only Y is closed. I told you while doing properties of topology, after defining topology and the properties of subsets, a set A is closed if and only if A bar is A. Now, first suppose Y is complete, prove that Y is closed. If you want to prove Y is closed, we prove that Y bar is Y. That means we prove Y bar is a subset of Y and Y is a subset of Y bar. Okay. So start with one element in Y bar. Suppose X belongs to Y bar. That, what do you mean by that? There exists a sequence Yn in Y such that Yn converges to X. This is what you mean by X belongs to Y bar. That means Y contains all of its limit points. That means there exists a sequence Yn converges to X. And you have Y is complete. Y is complete means it is a Cauchy sequence. Your sequence Yn is Cauchy. Because we know that what do you mean by complete metric space? In a complete metric space, every Cauchy sequence converges. So Yn is a Cauchy sequence. And Yn converges to X belongs to Y. So there exists Y belongs to capital Y such that Yn converges to Y, which implies you have X equal to Y. Because unique limit point, it will have unique limit point. That means you have X equal to Y means you have Y bar equal to Y. Means Y is closed. Conversely, suppose Y is closed. Conversely, suppose Y is closed. For this, we prove Y is complete. To prove Y is complete, we prove that every Cauchy sequence in Y is convergent. Let Yn be a Cauchy sequence. Yn is a Cauchy sequence in Y, hence in X. Okay. Now, given that X is complete, given that X is complete, so there exists X belongs to X such that Yn converges to X. That means every Cauchy sequence in converges to X. That means you have X belongs to Y bar, which is Y. This implies sequence Yn convergent in Y. Therefore, Y is complete. Just students go through this one. This is one important theorem. You have any doubts means I will explain once again. See here, a subspace Y of a complete metric space X is complete if and only if Y is closed in X. If and only if means we have to prove the theorem in two parts. First, suppose Y is complete. Prove that Y is closed. In order to prove Y is closed, you have to prove Y bar is Y. Now X belongs to Y bar means?
Ma'am, Y bar means complement?
Yes, Y bar is the closure of Y which contains all of its limit points, Y bar.
Okay.
Yeah. So Y bar, so there exists. See, what do you mean by X belongs to Y bar? Do you remember, Amma, what is A bar? A bar is A union D of A, derived set of A. A along with its limit points. Okay. So when do you mean, what do you mean by X belongs to Y bar? If there exists sequence Yn in Y such that Yn converges to X. Now, what is the assumption on Y? We assumed that Y is complete. Y is complete means every Cauchy sequence in Y converges. That means Yn converges to X.
Ma'am, convergence means how can we exactly imagine it to be
Yn
convergence?
converges to x means you have mod yn minus x. You have mod yn minus x is less than epsilon for all positive integers n greater than n naught. Okay.
That means how can we visualize that, ma'am? Not able to understand through the formula, actually.
Limit n tends to infinity, pi n is x. Ante, that means you see here.
Yeah,
How
with
to
a diagram.
yeah. See here. Suppose if you take the graph of function, suppose you take any 1 by x or 1 by x square, all the values are coming down, 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 and finally they will, large points, they approach to 0. Suppose if you take 1 by x square, you draw the graph. For a large values of n, it approaches to 0. If that means its the limit n tends to infinity, xn has a finite value, then we say that the sequence is convergent for large values of n. Now got it?
Okay. Yeah, ma'am.
That's
So
what
it is not 0, but closely
approaches to 0.
To 0.
For,
okay.
Yeah, for large values of n. Okay.
Yeah, yes, ma'am. Got it.
Suppose if you take limit n tends to infinity, you take, okay, you take like this 2n plus 4 by 3n plus 5. Okay, Andy? So how you find this limit? Limit n tends to infinity, we write like this, 2 plus 4 by n by 3 plus 5 by n. Okay. Can you simplify like this? I took n common. Okay.
Yes.
So for large values of n, this value is 2 by 3 and so that is the reason we can say that if you define a sequence 2n plus 4 by 3n plus 5, it converges to 2 by 3. Okay.
Okay, ma'am.
Like that.
Yeah.
So like that, if you take any Cauchy sequence is the other one. Cauchy sequence means, that means if you take the function values like this, the distance, whenever all the points are coming closer to each other, whenever points on x-axis are coming closer to each other, on y-axis also they will be coming closer to each other. That means mod xn minus xn less than epsilon. Okay.
Yeah, okay.
Emma, are you able to learn theorems from topology? Are you following? Hello?
Yeah, now I'm able to understand, ma'am. With like pictorial, if we understand, then it is easy to understand the formula.
Okay.
Otherwise,
Graphical representation is there means, yeah.
Yeah, graphical representation helps.
Okay. Actually, topology is the subject which is very dry. Okay. Some noise is coming. Keep your system in mute. Okay.
And topology, real analysis, very close, right, ma'am? It is on real numbers and this is on metric spaces.
Yes.
Okay. Yes.
Topology and real analysis, both theorems will be same almost. Okay. Anyhow, we are going to study about compactness, connectedness, separation. All the concepts will be same. Okay.
Yeah.
ఇలా చేస్తా వచ్చింది అది చూపించు. చాలా మటుకు వచ్చింది కదా. ఇది వచ్చేస్తుందిలే. ఇక్కడ 4 వేసుకో మళ్ళీ. ఇది 4 ఇది 4 ఇది 4 రావడం వల్లనే అప్పుడు నీకు ఇది 90 మైనస్ అవుతుంది. ఇది 90 ఇది 4 2c/2 cos c/2 వస్తుంది. ఇది 4. Hello.
Yes, ma'am.
Now we are going to find out the relationship between compactness and connectedness. Okay. When do you say that a metric space is compact? A metric space is said to be compact if and only if every open cover has a finite subcover. Otherwise, every sequence in X has a convergent subsequence. Okay. Now we are going to discuss about compactness and completeness. So this is one important theorem for 10 marks. A metric space is compact if and only if it is complete and totally bounded. Complete and totally bounded. A metric space is compact if and only if it is complete and totally bounded. See here, let us see. Before proving this theorem, just now let us revise the points, because you are getting in a, you are not able to understand. No, that is the reason. Once again, let me explain about compact sets definition and Lindelof spaces and all. See, because to prove Ascoli's theorem, this proof of this theorem is very, very important. We say that X is compact if every open cover has finite subcover. Every open cover has finite subcover. That means if X is equal to union G alpha, alpha belongs to delta, where G alpha is the set of all open sets, then you have G alpha 1, G alpha 2, so on, G alpha n is a cover for X. Then in such case, we say that X is compact. Okay. So what do you mean by finite intersection property? If every finite intersection property has a non-empty intersection, then we say that X is also compact. What is the finite intersection property? If there are finite sets in that metric space or in a topological space such that A1 intersection, A2 intersection, etc., intersection AN is non-empty, then we say that X is said to have finite intersection property. Okay. And what are the results we have learned? Any closed subspace of a compact set is compact, and continuous image of a compact space is compact. What do you mean by a continuous function? A function f is said to be continuous whenever mod f of x minus y, x minus a is less than delta. If you have mod f of x minus f of a is less than epsilon, that is, if d of x comma a less than delta implies d of f of x comma f of a less than epsilon, then we say that the function is continuous. And we have defined Beljanov-Weierstrass property. What is Beljanov-Weierstrass property? If every infinite subset of a metric space has a limit point, then we say that X has Beljanov-Weierstrass property. What do you mean by sequentially compact metric space? A metric space is said to be sequentially compact if every sequence in X has a convergent subsequence. If every metric space in X has a convergent subsequence, we say that X is sequentially compact. A plus B plus C is 0. You are getting answer? I check. Students, if you want to learn topology, what all the definitions that are coming, you write one by one, order one. First, what do you mean by topology? We say that the collection of sets tau is a topology. If empty set belongs to tau, X belongs to tau. Union of collection of sets again in tau. And intersection of finite subsets belongs to tau. Then after that topological space, what do you mean by open set, closed set? A set is said to be open set if every point is an interior point. A set is said to be closed. What do you mean by closed set? If A bar is equal to A. So all these results, all these definitions, you write on one paper. Then you first learn definitions. Without definitions, you cannot learn any theorem from this. A metric space X is said to have Beljanov-Weierstrass property if every infinite subset has a limit point. A metric space is sequentially compact if every sequence has a convergent subsequence. When do you say that a metric space is the total epsilon net? And what do you mean by epsilon net? If X can be written as union of S epsilon A. That suppose say a finite set A1, A2, etc. AN is an epsilon net if X is union I is equal to 1 to N S epsilon AI. That means you have S epsilon A1 union. Ante there is a open sphere centered at A1 or at each and every point of A1, A2, etc. AN. And a metric space is said to be totally bounded if it has an epsilon net. And we proved all these in offline only. I have proved these theorems. Any sequentially compact metric space is totally bounded. Okay. Now, we prove the famous Ascoli's theorem. And if you are able to learn this Ascoli's theorem, this is one compulsory question. Ascoli's theorem. To prove this Ascoli's theorem only, what are the requisites I taught you today? Again, I'll take the class from 3 to 4. Okay. Because yesterday I missed my class. Hello.
Yes, ma'am. Yes, ma'am.
Today I'll take one more class. To prove Ascoli's theorem, what are the requisites that are needed? What are the definitions that are required is a complete metric space. A metric space is said to be complete if every sequence is every Cauchy sequence convergent that. And what do you mean by Cauchy sequence? If for all n comma m greater than or equal to n naught, d of xn comma xm is less than epsilon. For 5 marks, this theorem is important, which is 9.3.4. Any metric space, every convergent sequence is a Cauchy sequence. Any doubt in proving this theorem?
No, madam.
You have
No.
d of xn comma x is less than epsilon by 2 because xn converges to x for n greater than or equal to n naught. Suppose in place of n, if you take d of xn comma x is less than epsilon by 2 for all n greater than or equal to m naught, n naught, m greater than or equal to n naught. Now you have d of xn comma xm is also less than epsilon. So every convergent sequence is a Cauchy sequence, and every Cauchy sequence is convergent because a Cauchy sequence is bounded. Every Cauchy sequence is bounded. Now in any metric space, a Cauchy sequence is convergent if and only if it has a convergent subsequence. Okay, next one. A subspace Y of a complete metric space X is complete if and only if Y is closed in X and Y is closed in X. Ante enti, you have Y is a subset of X. Now next one is, next theorem. A metric space is compact. A metric space is compact if and only if it is complete and totally bounded. It's అయిపోయింది. So first you take, let's suppose X is a metric space. X is a metric space with metric D. X is a metric space with metric D. And suppose X is compact. Okay, if X is compact, we prove that X is complete and totally bounded. This is what you have to prove. X is compact if and only if it is complete and totally bounded. For that, suppose we know that every compact metric space is sequentially compact. X is sequentially compact. X is that means sequentially compact means every sequence is convergent. That means you have every Cauchy sequence. When do you say that X is sequentially compact? Every convergent sequence has convergent subsequence. So you have every Cauchy sequence. If you take any Cauchy sequence, every Cauchy sequence has a convergent subsequence. That means By above theorem, you have X is complete. We proved just now, we proved that X is complete if and only if every Cauchy sequence has a convergent subsequence. So X is complete. And what you have to prove? X has an epsilon net. So you have X is complete. Also, for epsilon greater than 0, the set S epsilon X for every X belongs to X is open cover. Kada? This is an open cover. Set of all open spheres form an open set. So it is an open cover. That means, what do you mean? What is assumption on X? You have X is compact. X is compact means this open cover will have a subcover. That means X is covered by finite S epsilon X. That is, you have X is the union of I is equal to 1 to n S epsilon X. That means you have X1, X2, etc. Xn is an epsilon net. So you have X is totally bounded. Therefore, whenever a metric space X is compact, then it is complete and totally bounded. Okay. The next part I'll teach you in the afternoon. Afternoon we will finish Ascoli's theorem and the proof of this theorem. Okay, ma? Hello?
Okay, madam.
Any doubts on these concepts? Ask me now.
Ma'am, how can we say that a series will be always convergent? For example, if we take 1 by x power n, it will be convergent to 0. But if it is an increasing exponent like x power n or 2 power n, then it is converging to infinity, right?
Yes.
So, but now in the above theorem that we proved, so we took always it converges to x, y converges to x in the previous one.
Yeah.
So are we limiting the, is there any precondition that
yes,
x is a max?
Yes, I understood your doubt. Let me explain this one. See here, what he says, a subspace Y of a complete metric space X.
Okay.
That
Okay.
means
So X is a max superset and Y is a subset of X.
Yeah. X is set, Y is a subset of S. What do you mean? All the elements of Y are elements of X. But now all the elements of X need not be elements of Y. Okay.
Yes.
So that Y, what he says, a subspace Y of a complete in X, in X, all the sequences are convergent because it is a complete metric space. We say that X is complete if every sequence is convergent. Cauchy sequence means you don't get panic about it because every convergent sequence is a Cauchy sequence. Okay.
Okay.
So here what we have to prove, what all the properties satisfied by X, it should be satisfied by, we are checking. Suppose if X is complete, what about its subsets? All the subspaces of X are going to complete or not? Because all the elements of Y are elements of X. There are some elements of X that are not in Y. Am I right?
Yes.
So that is the reason what he says, you have Y is complete if and only if Y is closed in X. Y is closed in X means all the limit points of Y are in X. That means first you take Y is complete. What do you mean by Y is complete? All the sequences Y are converges in Y. That means if you have Yn is a sequence in Y, it is convergent in Y, which is a subset of X. So it is convergent in X also.
Yeah.
Okay.
Yes, yes.
So that is the reason you have Y bar equal to Y. Y is complete means Yn is a Cauchy sequence. That is Yn converges to X. X belongs to Y means X belongs to X also. Because a same sequence cannot have two limits. That means if you say limit n tends to infinity, xn is L, means this L is unique. You cannot have two limit points for the same sequence. Okay.
No.
So that is the reason you have Yn converges to Y means you have X equal to Y.
Yeah.
Suppose if Yn is a Cauchy sequence and Yn converges to X means your X is equal to Y. So you have all the Y contains all of its limit points. So Y is closed. Okay.
No.
Now conversely, suppose you have Y is complete. Y is complete means every Cauchy sequence converges in Y, means it is also converges in X. That means you have Y is complete. Okay.
Yeah.
That's all.
Thank you.
Any other doubts? This you understood? A metric space is compact if and only if it is complete and totally bounded. A metric space.
Yeah, can you explain once more if you don't mind?
Yeah.
Simple terms.
A metric space is compact if and only if it is complete. First, suppose XD is a metric space. Then a complete metric space, suppose we have to prove that X is complete. To prove X is complete, what is required to prove? Every Cauchy sequence has a convergent subsequence. We know that every metric space is sequentially compact, isn't it? In the previous classes, we proved that every metric space is sequentially compact. What do you mean by sequentially compact metric space? It is every sequence has a convergent subsequence. If every sequence has a convergent subsequence, if you take a Cauchy sequence, obviously it also will have a convergent subsequence. Okay. So you have X is complete. We assumed that compact and X is compact. Every compact metric space is sequentially compact. And then what you have to prove? You have to prove that X is also totally bounded. What do you mean by compactness? Every open cover will have a finite subcover. So for a compact metric space, what will be an open cover? The set of all open spheres and S epsilon X is an open cover. Since X is compact, every open cover will have a finite subcover. That finite subcover itself will form an epsilon net. What do you mean by epsilon net? It is S epsilon X1 union S epsilon X2 union S epsilon Xn. If you are able to write X as S epsilon union as X1 union S epsilon X2 union S epsilon Xn, then we say that X1, X2, etc. Xn is epsilon net. This is possible only because X is compact, and compact means every open cover will have a finite subcover. So you have every compact metric space is complete and totally bounded. Okay. In the next class, I'll take a complete and totally bounded metric space. I prove that X is compact. Okay, shall I leave? Hello?
Yes, ma'am. Thank you, ma'am.
Okay.